Hello, welcome to Advanced Composites. Today is the start of the second week of this course, and over the span of this week we will primarily cover the topic which helps us understand how do stresses change when we are also transforming the coordinate system, that is one, and also the stress strain relationship for anisotropic materials, orthotropic materials, especially orthotropic materials, materials with planar isotropy, and so on and so forth. So, that is pretty much the agenda for this week. A lot of this stuff which I am going to cover in today as well as this week's lectures, it has been described in great detail in the introductory course, that is Introduction to Composite Materials, but just for purposes of completeness I will go through all these topics over the period of this week a little bit fast, and in case you wish to learn more about some of these specific topics and their details, please go back and look at the lectures for Introduction to Composite Materials, which was the introductory course for composites. So, having said that, what we will start discussing today is stress convention. So, let us explain that. So, suppose I have a piece of material, and this is important because we will follow this convention. So, it is important to understand this correctly. So, this is a piece of material, and let us say I have three axes. This is axis 1, this is axis 3, and this is axis number 2. So, all these three different axes, they are mutually perpendicular to each other, and this block of material, which is rectangular block, it is experiencing several stresses. So, let us look at what kind of stresses this material is seeing. So, if I apply a tensile stress in one direction and it is applied on this plane, I call it sigma 1 1. Okay. So, why do I call it sigma 1 1? Because the first subscript, it refers to the direction of plane on which stress is applied, and the second subscript, which is again 1, is the direction of force. So, to specify any stress, we have to specify two directions. One is the direction of force, which is there in the second subscript, and the first one is the direction of plane. So, the direction of plane is this plane A, B, C, D, and what is its direction? Typically, whenever we talk about direction of a plane, we refer to the direction of the normal which is to that plane. So, the normal which is to that plane is direction 1. So, the first subscript refers to one direction because that is the direction of plane on which force is being applied, and the second subscript is direction of force in which the force is getting applied. So, that is why it is sigma 1 1. I can also apply another stress on it. So, sigma 1 1 is tensile stress, and the other stress could be shear stress, and once again because it is a shear stress, I designate it by letter tau, and the first subscript is 1 because that is the direction of plane on which the stress is being applied, and the second subscript is 2, which relates to the direction of the force in which this stress is being applied. Similarly, I can also apply another shear stress which is in this direction, which is again parallel to this plane, and once again it is a shear stress. So, I designate it with letter tau. First subscript relates to the direction of the plane. So, that is still 1, and the second subscript relates to the direction of the force, and this force is getting exerted in 3 direction. So, it is tau 1 3. So, let us do it couple of times more. So, let us consider this plane, and the normal stress will be in this direction, and because this is the normal stress, I call it designated by letter sigma, and then it will have again two subscripts. The first subscript will be the direction of the plane on which it is getting exerted. So, it is getting exerted on plane E A D F, okay, and the direction of normal is 3. So, the first subscript is 3, and the second subscript tells us the direction of the force. So, that is also 3. So, sigma 3 3. Let us look at shear stresses on this plane. So, this is one shear stress. So, what is this shear stress? How do we designate it? We designate it by letter tau, okay, and it will have two subscript. First subscript relates to the direction of the plane, second subscript relates to the direction of the force, which is 2. And then there is another shear force which can get exerted on this plane, and that is tau, because it is a shear stress. First subscript relates to direction of plane, and second subscript relates to direction of force, which is 1. And then we will do this one last time. So, we are talking about plane E A B G, and the normal stress will be sigma 2 2, and then there could be a shear stress, and that shear stress is tau 2. 2 is the direction of plane and direction of force is 1. So, tau 2 1. So, and then we have another shear stress, and we designate it as tau because it is shear. First subscript is 2, which is direction of plane, and the second subscript is 3, which is the direction of the force. So, this is the convention. Okay. So, this is how we will designate stresses in the whole course. The next thing I wanted to talk about is this concept called tensors. Tensors. Okay. So, in general, tensors are entities which are associated with one or more directions and have a magnitude also. So, this is not exactly the mathematical definition, but this will help you understand the concept. Now, you may be wondering that if this is what tensors are, then how are they different from vectors? So, that is what we are going to discuss. So, the key thing is that they may be associated with either one direction or another more sets of directions. Now, if we consider force, right. So, let us say this is force, the length of this vector is the magnitude of the force, and the direction of this arrow designates the direction of force. So, this force is associated only with one particular direction. So, in that sense force is also a tensor. In that sense force is also a tensor. We can also call it a vector because vectors also are associated with a direction, but in case of vectors the dependence on directions is only one. So, force depends. So, when we define force we only have to specify one set of directions. We do not have to specify two sets of directions or three sets of directions or four sets of directions. So, in that sense force is a tensor, and it is a special tensor because it is associated with only one set of directions, and because it is associated with one set of directions it is called first order tensor. It is called first order tensor. Further, it is first order tensor, and first order tensors are also known as vectors. Okay. They are also known as vectors. Let us consider mass. Now, mass is not associated with any set of directions. So, it is 0th order tensor, and 0th order tensors are also called scalars. So, in that sense tensors are general entities, they incorporate vectors, scalars and higher order tensors. Now, we will look at couple of tensors which are associated with not just one set of directions, but two or more than one set of directions. So, consider stress. Consider stress. Now, we have shown earlier that whenever we talk about stress as a tensor, what do we have to do? So, suppose we are saying that it is shear force on this plane, and let us say this is my axis system 1, 2 and 3. So, whenever we specify a stress, we specify two things. We specify the direction of force. So, whenever we specify a stress, for instance in this case shear stress, what do? We specify its magnitude, we also say that it is what is the direction of the force. So, this is one thing we specify, and we also specify the direction of plane on which it is acting. Okay. We have to specify all these three things. We have to specify magnitude, we say it is so many megapascals, 30 megapascals. So, 30 is the magnitude. We say that it is shear stress on plane A, B, C, D, and the moment we say it is shear stress on plane A, B, C, D, we are specifying that what is it we are specifying? We are specifying the direction of the plane. So, we are saying that it is 30 megapascals, it is a shear stress, and the plane on which it is acting is plane 1. Okay. And then we also have to specify in which direction the force is acting. So, in this case the force is acting in, so this is 3 direction and 2 direction. So, force is acting in 2 direction. So, it is tau 1 2. Okay. So, stress, because of this we have to specify two independent set of directions. The direction of the force does not get influenced by direction of plane on which it is acting, and vice versa. So, this 1 and 2 are independent set of directions, they do not influence each other. Okay. So, when we specify stress, we have to specify the magnitude, we have to specify the direction of the force, and we have to specify the direction of the plane on which the stress is getting acted upon. And because we have to specify two independent sets of directions associated with shear stress tau 1 2, we say that stress is a second order tensor. It is a second order tensor. So, whenever we specify stress, it is a second order tensor. Unlike stress, pressure, it is a 0th order tensor. And why do we say pressure is a 0th order tensor? Suppose there is a complicated cavity, and the moment we say that the pressure inside the cavity is, let us say 50 MPa, it is implied the moment we say that at every point the force per unit area in the direction normal to the surface, whatever the normal is, in the direction normal to the surface is 50 MPa. So, here we do not have to specify, it is by default, it is already known. The moment we know the surface, the direction of the force is also defined. Okay. So, that is why it is a 0th order tensor, but stress is a second order tensor. So, stress is an example of second order tensor. Another example of second order tensor is strain, and we will explain that in couple of minutes why that is the case. So, suppose consider the case that I have a block of material and I pull it, and as I pull it, it will become a little bit longer and also a little bit narrower if this material is isotropic. So, if I pull it, then extensional strain will stress will only produce extensional strains, as we discussed last week. So, when I say that this body is going to experience a strain, what is the definition of strain? It is extensional strain. For instance, if this is my L direction, this is my T direction, and if it is pulling getting stretched in the longitudinal direction, then epsilon L is defined as del u over del x. Okay. So, there are two directions in this relationship. One is the direction of displacement, and this direction has to be in the direction of x, only then it will be defined as epsilon L. If it was del v, which is in the transverse direction, then it would not be longitudinal strain. Okay. So, this is the, so u is associated with the direction, u displacement is associated with the direction, and also the direction in which I am computing this differential is also the other direction. So, I am computing the differential of u with respect to x direction. So, there are two directions embedded in this formula. First is direction of displacement, and the second is direction in which differential is being calculated. Okay. So, these are two directions. Another example of strain would be, suppose I have a piece of material and let us say just I apply some force on it only on top and bottom surfaces. Just assume, although it is physically not possible, that there is no force on these vertical sides. So, what will happen? And if it is isotropic material, what will happen? It will become something like this. So, if it is a rectangle, it will become something like a parallelogram, and when it becomes a parallelogram, this angle initially was 90 degrees or 0 degrees, this becomes some non-zero angle, right. Now, if this is my L direction, this is my T direction, then the displacement, let us say the top surface, let us say the top edge is AB, AB is moving out, okay. AB is moving out, and if I want to compute shear stress, shear strain, then the relation for shear strain gamma LT is del V, and V is the displacement in y direction, over del x plus del u over del y. Okay. Now, just think, so just for a moment do not think about this one, let us just focus on this. The top surface is moving in L direction. So, point B moves to B prime location, right, and what is y? Y is this direction. So, I am computing the differential of displacement u with respect to y axis. Okay. So, this is direction of displacement, and this is direction in which this gradient or differential is being computed. So, once again this gamma LT, if you look at the second component, it is associated with two directions. Similarly, del V over del X is also associated with two directions. So, strains are also having associated with two mutually independent set of directions, and that is why strains are also second order tensor. They are also second order tensors. And then finally, we will look at E. So, if a stress is a second order tensor, in general I can express it as sigma ij, right. If a strain is a second order tensor, then I can express it as epsilon KL, where I and j, all of these could assume values of 1, 2, 3. 1 could be x axis, 2 could be y axis, 3 could be z axis, and so on and so forth, right. So, this is a second order tensor, and that is why it has two subscripts. Epsilon KL is also a second order tensor, so it also has two subscripts. Now, it turns out that Young's modulus or elasticity constant is a fourth order tensor. Example, what is Young's modulus? Young's modulus is what? It is for isotropic materials, we have this Young's modulus and we call it E, and what is it? It is sigma 1 1 divided by epsilon 1 1, right. So, strain is a second order tensor, stress is a second order tensor, and in this case Young's modulus is a function of two second order tensors, and all these directions are mutually independent. The first subscript in sigma relates to the direction of plane, which has nothing to do with all the other three directions. Second subscript in sigma is direction of the force, which has nothing to do with all other three directions. Third subscript, that is epsilon, in the first subscript of epsilon is the direction of displacement, and the other second subscript is the direction in which we are calculating the differential. So, all these four directions are mutually independent. Okay. It is not that if you know one you can figure out the other one, you have to know all four of these. So, E or elasticity constants, they are fourth order tensors. So, I am just explaining this in this way. Okay. So, E is a fourth order tensor. So, we give it 4 subscripts E I J K L in general, okay. And the relationship between stress and strain for this E I J K L is sigma I j equals summation of E I J K L epsilon K L, and you sum it twice. So, first time you sum it on index L is equal to 1 to 3, and the second time you sum it on K is equal to 1 to 3. So, this is the stress strain relationship, and this stress strain relationship is linked through this elasticity tensor. Stress is a second order elasticity tensor, strain is a second order elasticity tensor, stress is a second order tensor, strain is a second order tensor, and strain times elasticity, which is a fourth order tensor. When you multiply and add up all the individual products, you get sigma I j. So, this is important especially in context of composite materials, because in case of isotropic materials, if you try to find the Young's modulus in x direction or y direction or z direction or any other direction, it just turns out, because of mathematics and physics involved, that E 1 1 E in all the directions is same, but the same may not be true for anisotropic materials. So, we have a much more complicated and sophisticated model for relating stresses and strains in context of anisotropic materials. So, in the next class we will start discussing how do we handle these elasticity constants and so on and so forth. So, that is all, and we will meet tomorrow at the same time. Thank you.